Hey, it's Mr. Shrum, and welcome to the first video that I'm going to upload to the homepage. And it is the introduction to the physical sciences. So let's get into it. And in this lesson, we're going to explain the nature and importance of the physical sciences specifically. So for a warm up, it asks you, okay, which of these things is considered a science or a branch of science, and what is not science? So we have astronomy, biology, geology, physics, and chemistry over here on science side. And then not science, we have astrology and theology. Okay. So these are branches of science, and the study of these topics follows a very specific process of observation, reasoning, testing, analyzing, and concluding. What can we conclude from our observations and analysis? While astrology and theology, they're not scientific. They are fields of study. Well, uh, I guess I just won't comment anymore about astrology. It's fun, but it's not science. The nature of science. All right, so science. Everybody's heard the word. So, what is it? Well, it's the study of the natural world and how it functions. Scientists, crazy guys, and girls, of course. Scientists conduct this study through observation and experimentation. Very curious folks get into science. Science involves investigation. You're investigating nature, and that can involve you going into the field and make direct observations of natural phenomena or collect samples to study. So, say you're wanting to plant a garden in an area, well, you would test the soil and test the water source nearby if that's how you're going to water the garden. But those tests and collecting samples help scientists get a better understanding of their environment, what they're working with. And at other times, it may require lab work in which scientists conduct experiments to test an idea under very controlled conditions. So you have field work, which is in more of a natural environment, reality as it is. And then scientists may control conditions to such a degree that you need a lab. Science is also the body of knowledge built on the results of past investigations. So all the work past scientists have done is built on even older scientists before them. And this knowledge is passed on and on and on and improved by each generation. Before carrying out new observations and experiments, it's useful to know what scientists have already discovered. So by studying science, we learn how to carry out scientific investigations, and we also learn about what others have discovered through their investigations. So science is a very social and collaborative process. Um, and here we have the branches of science. We have the biological sciences like botany, ecology, zoology, physical science, which is the primary focus of this class. We have chemistry and physics. And then we have earth and space science, geology, astronomy, and meteorology. Now, there's a lot of cross pollination here. There's chemistry in botany and and ecology in chemistry and astronomy and physics, and they double dip a lot. And sometimes you see that people use the term science and technology interchangeably. It's important to understand the difference between these terms. The goal of science is to learn about nature, and technology is the use of scientific knowledge for a practical purpose. So, the way I think of it is science learns about the way nature is, the way the world works, and then engineers, technologists apply those principles and those theories and try to create practical solutions to our problems. And an example is it of this, excuse me. Through observation and experimentation, scientists learn that hot air rises and cool air sinks. That knowledge, that is scientific knowledge. Engineers used it to develop the technology to heat and cool air in a controlled environment. They applied this technology to create hot air balloons that could take people and objects high up in the air and then bring them down again safely, thankfully. All right, so this slide is about statements and what is classified as scientific and what is not scientific. Scientific statements are questions that science is able to answer or investigate. So a statement is a scientific statement only if it is possible to prove it wrong. Another way to say that is it's falsifiable. If something is not falsifiable, it's not scientific. It's simple as that. So any subjective statement like low-pitched sounds are better than high-pitched sounds. Basically, I like low-pitched sounds more than high-pitched sounds. I can't prove you incorrect, right? And you can't prove me incorrect about if I disagreed with that statement. It's non-falsifiable. So interest, taste, classical music is the most beautiful. This is not something you can investigate in a lab. Alien life forms visited Earth in prehistoric times. Yeah, I guess you would need to investigate before you make a statement like that. Scientific statements, water boils at 100 degrees Celsius. You can check that out and see for yourself. Sugar dissolves in oil. Red light causes plants to flower more quickly. So these statements can be disproved or verified and supported with evidence. Non-scientific statements, they just can't handle that type of pressure. All right, a question. Which statements are scientific statements? Oh, well, I gave you the answer key. Oops. People who drive red cars are more prone to accidents. So you can test that out. Children from families that have pets are more likely to develop allergic reactions. People who walk to work are healthier than those who commute to work in vehicles. So you can picture experiments taking place where scientists are observing and analyzing and concluding. On the other hand, Chinese cuisine is tastier than Mexican cuisine. Besides that being like just a crazy statement, and I love Chinese and Mexican cuisine, they're not tastier than the other. Or those in the younger generation should learn to respect their elders. Oh man, so every generation says that about the younger generation. It's a tale as old as time, and the tale as old as time is non-falsifiable, so it is not scientific. And it's a silly thing to say in the first place. All right, but that is all to get to the scientific method. To support or disprove the statements or the scientific statements, we follow the scientific method. This established process can take many forms, and the image here, let me zoom in a little bit. There you go. And this is one possible sequence of steps. Sometimes there's more, sometimes it's a little more simplified than this. But here, we'll read it. So, it begins with observing a phenomenon in the natural world. The next step is to question the observation and to think about a logical explanation. And this logical explanation, this plausible explanation, is derived from observation. And we call this a hypothesis. It is a proposed explanation for an occurrence based on available data we have, observations we've made, or other types of evidence. Testing the hypothesis is the next step, and that may involve collecting data like soil samples, water samples, or conducting experiments on the phenomenon or investigations. The last step in the process is analyzing the test results to determine if the hypothesis is true. After reaching a conclusion, communicate the results. If the hypothesis was found to be false, it may be appropriate to revise the hypothesis and run a similar experiment to test the new hypothesis. So remember that the scientific process may take different forms depending on the subject of study, but the main structure remains the same. And in your own life, you've been a scientist. You've noticed something. You wondered about something. All right, what caused that thing to happen? You used evidence, observations to construct, some teachers say educated guess, but you are proposing an explanation, a hypothesis for why something occurs. And then sometimes you test it out and see whether you were right or wrong. You know, it's a very basic thing, but it's gotten us so far. All right, so scientific knowledge. What have we been able to find out through using the scientific method? What does it mean when we say that something is scientifically proven? Is that a thing to say? Well, scientists can't actually prove a theory. That's not the type of language we use in science. As scientists conduct repeated experiments, they simply become more confident that their theories are correct. Scientific knowledge is always being refined and improved in this manner. For example, when white light passes through a prism, many different colors of light emerge from the other side, seen here. Scientists initially believed that the prism adds color to the light. However, Isaac Newton, you may have heard of him, he performed several experiments, as well as many other scientists since Newton's time, point to a better explanation. Watch the following video to learn about one of Newton's physics experiments that led to a better understanding of the nature of light. Let me turn on the captions. And share soon. I think it's copywritten. So I will upload this to YouTube, and then I'll post this in the page. To get around that, silly BBC. There are 3 types of scientific knowledge. For example, a statement that describes an observed pattern is different from a statement that explains why the pattern occurs. A scientific statement may take the form of a fact, hypothesis, theory, or law. I say 3 different, I just meant there are different types of scientific knowledge. A fact is something we can observe directly. Different people observing the same object or occurrence would agree on the fact. For example, the knowledge that copper metal expands when heated is a fact. You can observe it. Whereas a hypothesis is a proposed explanation that may be found to be true or false by experiments. If it is found to be true, the hypothesis may then be considered a fact. A prediction that copper will expand more than iron when they are heated to the same temperature is a hypothesis. Because you're taking a fact, if you heat up copper, it will expand. And then you're proposing an explanation. Copper will expand more than iron. A scientific law states a recurring pattern of behavior, but it doesn't explain the reason for the behavior. It describes how a certain part of nature always behaves in certain circumstances. A hypothesis may become a law if it is tested repeatedly and never contradicted. Many laws can be stated mathematically. So, for example, we have Newton's second law of motion, stating that the net force on an object equals its mass times its acceleration. F equals ma. A theory is an explanation for many observations. A theory explains the reason nature behaves the way it does. For example, the atomic theory states that substances are composed of indivisible particles called atoms. And this theory helped 19th century scientists, so I think 1800s, explain why different substances react with each other in certain ways. Theories and laws are different types of knowledge. A theory cannot become a law, and a law cannot become a theory. They achieve different things. A theory explains why something is the way it is in nature, and a law just describes pattern. Pattern recognition is law. Theory is trying to explain the pattern. So we have another question here. Atoms are made up of protons, neutrons, and electrons. That is a theory. Energy can be neither created nor destroyed. That is a law. Water freezes at 0 degrees Celsius. That is a fact. And here's the easiest one, I think. If a piece of platinum is placed in acid, it will not react. So if statements sounds like a hypothesis. Theory, atoms are made up of protons, neutrons, and electrons. And that helps explain the way nature exists in reality. Whereas energy can be neither created nor destroyed. That is a recognition of pattern. Certainty in science. After a scientific theory is established, scientists continue to test it. If at any point the experiment results contradict the theory, then scientists must either discard the theory itself, or you have to modify it. So you either throw it out altogether, or you change it to accommodate the new results. No scientific theory is ever proved, because it's always possible that new evidence may contradict a theory. However, scientists will have a lot of confidence in a theory that has been tested rigorously and never contradicted by evidence. So everything can be proven, not proven wrong, but new evidence may contradict a theory. However, if something's never been contradicted for quite a while, it's a very strong theory. So an example of this is the phlogiston theory of the 1600s. Scientists of the time believed that substances that could burn or rust contained a weightless substance they called phlogiston. And they believed that once you burn this or rusted, this substance released its phlogiston into the air. Phlogiston. A fixed amount of air could absorb a fixed amount of phlogiston. I think that's the best way to pronounce it, which explained why the material stopped burning when the supply of air was restricted inside a closed container, for example. And then in 1775, a chemist named Antoine Lavoisier heated mercury inside a sealed container. This process produced a substance that Lavoisier knew as mercury calx. Lavoisier found that the increase in the mass of the mercury as it reacted was precisely equal to the decrease in the mass of the air in the container. This finding meant that the mercury absorbed a substance from the air. The change in the mercury was not a result of it releasing phlogiston, as scientists had believed. Rather, it was a result of the mercury absorbing a substance. Lavoisier believed this substance must be an element, and he called this element oxygen. Through Lavoisier's discovery, the theory of phlogiston that scientists had believed for more than 100 years was discarded. So there's an example of something being considered true or a very strong theory for 100 years, and then it was contradicted and they threw it out. So nothing is sacred in science besides the scientific method itself. The current scientific verdict on the phlogiston theory demonstrates which two of the following principles. An experiment can disprove a theory that scientists have accepted, and scientific theories can be replaced by better theories. The whole point of science is to get better at explaining phenomena. And sometimes you get it wrong, and that's just part of the journey. Careers in science. So we have a nice little section about forensic scientists. So imagine this. While watching the local news, you see a report of vandalism committed at a drugstore. The owner thinks it's an ex-employee. The closed circuit camera footage shows that the culprit was masked and wore gloves. So a visual identification is not possible. They have to identify the suspect using other evidence, and they will need to conduct lab tests on the materials found at the crime scene to link them to the crime or the culprit. So people in charge of this phenomena are forensic scientists, and they use various scientific techniques to carry out the lab work required in their jobs. Yeah, I'm sure you've all seen shows. Dexter comes to mind. I know he's like a blood work type of guy. Their jobs may also require them to serve as expert witnesses in trials to provide expert testimony. Other responsibilities include communicating between the crime investigators and the forensic lab. So, in this position, forensic scientists must have critical thinking and problem-solving skills to come up with a hypothesis and methods to test the hypothesis. And they also require good deductive reasoning skills. So let's say you're a forensic scientist called in to assist in this vandalism case. You may be asked to conduct tests on certain microfibers and confirm whether the fibers are from a pair of gloves recovered from the suspect's house. They would definitely need a warrant for that, but we'll just move past that. The task may involve conducting a chemical analysis of the dye present on the fiber in the gloves and determining whether they're the same. Christy is a forensic scientist. She is given a white powder and asked to determine whether it's sugar. She analyzes the white powder with a mass spectrometer in her lab, and we'll get into mass spectrometry, mass spectrometers later. But the test results reveal that the substance has a different molecular mass than sugar. What do these test results say about the initial hypothesis, and what would be a reasonable next step for Christie's investigation? The white powder is not sugar, so Christie's hypothesis is incorrect. Christie's next step should be to identify substances that have the measured molecular mass. And to read the explanation, if the powder had been sugar, its molecular mass would have been the same as that for sugar. Since they weren't the same, the initial hypothesis is incorrect. Christie could identify other white powdery substances that have the same measured molecular mass as the unidentified powder. With that list of possibilities, she can conduct additional tests to see if the collected substance has the same properties as any of the substances on her list. So think of white powdery substances. I'm sure you can think of a few. Moving on, working together in science. Scientific research is a collaborative activity. Scientists usually work in teams. Even a scientist who appears to be working alone usually relies on the work done by other scientists. Actually, all scientists depend on the works of others. No man is an island in science, or woman, or anything in between. Scientists follow a peer review process to reduce the number of errors that might occur in scientific experiments. Before a scientific report is published, it is sent to several peers or other scientists who work in the same field. These scientists provide feedback on the report. If necessary, the research scientist who authored the report may revise it and resubmit it. The peer review process ensures that only studies that follow good scientific processes and that draw valid conclusions are published. Because you can see a lot of nasty science, disingenuous scientists try to publish stuff, and that usually gets shut down unless a certain journal likes to publish that type of stuff. And scientific consensus. Scientific consensus is when scientists often try to repeat other scientists' experiments just to test each other. If different teams of scientists get the same result, then scientists will recognize the original results as valid. And scientists don't always agree on scientific theories, but if most scientists agree that a certain theory is likely correct, then they have reached a scientific consensus. A scientific consensus isn't exactly correct. Sometimes further experiments may show that an unaccepted position held by a minority of scientists was the better position. However, for the vast majority of things right now, there is consensus. Bias. According to the article, which of the following may be affected by a scientist's bias? Well, here's the article. I'll open that up. Views on bias can be biased. Men and women have different takes on studies of gender bias. Gee, that's really surprising. That's not really that surprising. But we can read through that at another time. But in that article, which of the following may be affected by a scientist's bias? Well, how they interpret experimental data, could bias them. The conclusions they draw from an experiment could be bias. How much they trust the work of other scientists, that could also be bias. So, scientific studies are based on observation and the collection of data. Scientists must analyze the data, objectively interpret it, and then draw conclusions. Here's the thing, though. Scientists are human beings, and they have implicit biases that may affect how they interpret things, what conclusions they draw, and their acceptance or suspicions about other researchers' work. Humans, beautiful creatures, but very flawed we are. Research bias. Many factors affect the results that scientists obtain from an experiment and the way they interpret those results. One such factor is bias, and a bias is a strong inclination about something that affects the behavior or mindset of a person. Let's look at two types of research bias. Confirmation bias. This occurs as a result of people's tendency to readily accept only evidence that confirms their beliefs. For example, let's assume you believe that you can't concentrate without listening to music. So you study for an upcoming test, listening to music, and score well on the test. You credit the result of your score to the concentrated effort you were able to put in because of listening to music. You may not consider other factors that contributed to your success. So this is kind of like a blind spot where you're assuming something occurred because of something easily identifiable, but that's not always the case. Selection bias is another type of bias, and this is a result of poor sampling techniques. It occurs when the result obtained from a sample of the population under study are different from the results that could have been obtained if the entire population had been considered. And an example would be, suppose that scientists want to measure the average mass of an iron atom. If they test only iron that came from a particular location, the results may not accurately represent the average mass of iron atoms all around the world. So, if the scientists use a method that tests samples from random locations on Earth, their results likely would be more reliable. Scientists cannot completely eliminate biases. Both confirmation bias and selection bias creep in unintentionally. However, scientists must take appropriate steps to minimize the potential for bias in a study. So a lot of times they will use blind studies or double-blind studies where they don't know which group is being affected by what. So it's sort of like keeping secrets from yourself, and designating certain people knowing, of course, but maybe the people directly involved don't know, so they cannot influence the experiment one way or another. Confirmation bias based on a person's own belief, selection bias caused by poor sampling techniques during experimentation. Both can be controlled but never eliminated. They are both a type of research bias. They both can affect the way a scientist interprets experimental results, and they're both unintentional for the most part. You know, there are a few disingenuous people out there trying to disprove things in their own favor, especially if there's money to be made. But that is the end of the introduction to the physical sciences tutorial. Let me know if you have any questions. And until next time, see ya. Have a good rest of your day.